Welcome back. Today a short, very practical engineering exercise. How to pick the right transmission carrier for a real backbone link. Here is the setup. We are designing a backbone link between two cities. The traffic on this link consists of two streams. First, 60 voice telephone channels, point-to-point trunks for the local exchanges. Second, one full television channel, a continuous video broadcast feed riding the same link. 3 questions. Part A. How much total bandwidth do these two streams demand together? Part B. Which member of the European e-carrier hierarchy is the smallest one that fits? Part C. How much spare capacity is left over once we install that carrier? Before we start picking, let us put the e-carrier ladder on the table. 5 rungs. E1, 2.048 megabits per second, 30 voice channels carrying 64 kilobits each, plus 1 signaling channel and 1 synchronization channel. That is what fills the frame. E2, 8.448 megabits per second, 4 E1s bundled together, 120 voice channels. E3, 34.368 megabits per second, 16 E1s, 480 voice channels. E4, 139.264 megabits per second, 64 E1s, 1,920 voice channels. And E5, 565 megabits per second, the top of the ladder. Each rung is a multiple of the one below it. When you pick a carrier, you do not get to pick a custom number. You walk up this ladder until your traffic fits. Part A. First stream, voice. A single voice call digitized for transmission requires 64 kilobits per second. The reasoning behind that number is exactly the Nyquist plus PCM chain we have used in this course. Voice spectrum tops out at 4 kHz. Nyquist says we must sample at twice that, so 8,000 samples per second. PCM codes each sample as 8 bits to keep quantization noise low. 8,000 samples per second times 8 bits per sample equals 64 kilobits per second. 60 channels, each at 64 kilobits per second. Total voice bandwidth equals 60 times 64, which is 3,840 kilobits per second, 3.84 megabits per second. Comfortably small. Part A continued. Second stream video. One analog television channel occupies 6 MHz of bandwidth. Apply Nyquist. Sample at twice that, so 12 million samples per second. PCM coding at 8 bits per sample gives 96 megabits per second per television channel. If the receiver needs 10-bit quantization for higher quality, the rate climbs to 120 megabits per second. But for this problem, we use the standard 8-bit value, 96 megabits per second. Add the streams up. 3.84 megabits for voice plus 96 megabits for video equals about 99.84 megabits per second total. Notice immediately how dominant the video is, over 96% of the total, and the voice is the round-in noise. This is the typical asymmetry whenever video shares a link with anything else. Part B. Picking the carrier. We walk up the ladder. E1, 2 megabits, does not fit. Our voice alone almost equals it. E2, 8 megabits, does not fit. Voice plus video need over 100. E3, 34 megabits, closer, but still far short. The video alone overflows it. E4, 139.264 megabits per second, finally fits. We need 99.84. We have 139. Part C. How much headroom? 139.264 minus 99.84 equals 39.42 megabits per second of spare capacity. Utilization is 99.84 divided by 139.264, which is roughly 72%. Healthy. What can we do with the spare? Another TV channel needs 96 megabits, does not fit. But we could load the headroom with data, file transfers, signaling overhead, or a few hundred extra voice channels. Or we keep it as engineering margin for traffic peaks. 3 engineering takeaways. 1. Capacity planning is ladder climbing. You do not get to order a custom-sized pipe. You compute your aggregate traffic and pick the next available standard rate above it. That is why hierarchies like eCarrier and SDH exist. They make pricing, multiplexing equipment, and interoperability tractable. 2. Utilization between 60 and 80% is the sweet spot. Below 60%, you are paying for unused capacity. Above 80%, your link starts queuing during traffic peaks and quality of service degrades. 72%, like our example, is exactly where you want to be. 3. Video dominates mixed links. One uncompressed television channel is roughly 1,500 voice calls in raw bandwidth. The moment a video stream joins a link, the voice budget becomes a footnote. This is the underlying reason why every video service in the real world is compressed. MPEG, H.264, AV1. They push that 96 megabit raw PCM figure down to 4 or 5 megabits, and suddenly the asymmetry vanishes.